Okay, a very good afternoon to all of you. On behalf of Jigyasa and CSIR-IMMT, myself, Dr. Manas Kumar Dalai, welcome you to the auspicious event ISS 2021 Jigyasa Outreach Program. So very soon, India is going to celebrate India International Science Festival IISF 2021 during 10 to 13 December at Panaji, Goa, and is being organized by Ministry of Earth Sciences, Government of India, Department of Biotechnology, Government of India, Department of Science and Technology, Government of India, Department of Scientific and Industrial Research, Government of India, Government of Goa, ICMR, New Delhi, and Vigyan Bharati, Viva India. India International Science Festival is an initiative of Ministry of Science and Technology and Ministry of Earth Science of Government of India in association with Vigyan Bharati, which is a science movement with Swadeshi spirit led by eminent scientists of the country. The main purpose of IISF is the celebration of science by all, engagement of common people with a science in a joyful and entertaining manner is essential for the healthy, prosperous, and meaningful life. Through its creative programs and activities, IISF provides opportunities to people and scientific fraternity in the country and abroad to come together, work together, and experience the joy of doing science for the well-being of India and humanity. Outreach program in the development of science and technology has great impact in the society to bring awareness in general public, among students of school, colleges, universities, teachers at different levels, and scientific fraternities too. To grace this auspicious event, we have with us Professor Vedang Das Mahanti from Niger, Bhubaneswar as our chief guest and today's keynote speaker. Mr. Vivekananda Paiji from Vigyan Bharati as our guest of honor. Professor Sudhasutto Vasu, Honorable Director, CSR Institute of Minerals and Materials Technology, Bhubaneswar. Dr. Devi Prasad Das, Coordinator of Jigyasa Program at CSIR-IMMT Bhubaneswar. And Dr. Vikas Kumar Jena, Principal Scientist at CSIR Institute of Minerals and Materials Technology, Bhubaneswar. With this, now, may I request our respected Director, Professor Sudhasutto Vasu, to kindly address the audience. Sir, please.
Very warm welcome to all the delegates and all the participants of Curtain Raiser program of IISF 2021 and the Jigyasa team of CSIR-IMMT who is organizing this Curtain Raiser program of IISF 2021 at the IMMT. I really appreciate the team Jigyasa of IMMT to organize this program, especially in the current scenario when there is a lot of obstruction and to do things because of physical proximity. Many cases is very much limited because of the current pandemic situation, although it's quite improved at the moment. Dr. Devi Das, who is the coordinator of Jigyasa program, is present here. Dr. Vikas Jena is also the program coordinator here, and Dr. Manas Kumar Dalai. And obviously the coveted guests who are here today, and our special guest is Professor Mohanty from Niger. He is a very well-known scientist in India and world. And then Sri Vivekananda Pai, who is a very active member from IISF and also in our He is presenting Vigyan Bharati, and so this All India Secretary of Vigyan Bharati, and I welcome Mr. Vivekananda Pai for coming here in this program through online mode. This is certainly a curtain raiser program, but the importance of the program is, of course, they create an awareness of science or STEM, science, technology, engineering, and mathematics, and everything, I would say, to the young children who are going to the school, young boys who are going to colleges and engineering colleges, or science and mathematics, those who are learning, create an awareness that what science and technology, engineering can do to our daily life. That research and development is very important, and through that only we can have a better life. Pandemic situation really taught us that how important is the biology, and with that, of course, there are many other streams are connected. Just doing biology will not work, because if you have to create a vaccine, after creation of vaccine, the application of the vaccine, the efficacy of the vaccine, the storage of vaccine, and then at the end, once it is agreed that this vaccine works, then you have to produce vaccine in billions and billions and billions in number. That means you have to know the process or upskill the process. So an engineer, a chemical engineer or a mechanical engineer can only take this, or a biotechnologist or biochemical engineer can take this forward to make billions on billions of vaccine in a short period of time, which is even falling short for the demand that we have all over the world. So, in a nutshell, it taught us recent pandemic that's of R&D just because of COVID-19, but otherwise also it is very well known that if you see the history of mankind, those who were doing well as a nation, they did really well as an R&D. They really did well in R&D and development, using of R&D in daily life. We do R&D and then we publish paper, and then leave it like there as a paper or documentation will not only will not help us. We also require to apply that R&D or innovation that we have brought in into our daily life, where we really lack. In our country, we lack in this front compared to the developed country, where they not only do fundamental science and technology development, they take it to the industry for and they do translational research, where the fundamental science and technology can be applied for human being upliftment of their livelihood. So in that part, we really we are falling behind, and we are trying to, of course, now the importance is known, and all of us are now trying that whether we have a product which is coming off your R&D work, and whether that can be useful to the humankind. So all these important part, and economics is also equally important. Not only that your product comes, the product should be sellable and should be technologically, specifically, or its specs should be as comparable, if not better, than what is available in the market. At the same time, it should be also cost effective or maybe cheaper compared to what product is there in the market. If you are already competing with the available product, then you have to be really better, both quality and in terms of cost. If you are the first one to bring it out, obviously then you have some luxury of economics, because no one else brought that product, and all these things need to be taught to the students, even from the class 7 and 8 to 9 and 10 to 11th and 12th, and then of course whether BSc, MSc, or it is BTech, MTech, PhD, all the phases, people need to learn the importance of economics. And IISF is one of such occasion through which we can create an awareness among the students community, among the research community, among the faculty members, to know that importance of R&D and importance of R&D in real life application and bringing them to the common people for the betterment of human life. So I really thank that our guest, Professor Mohanty, Shri Vivekananda Pai from Vigyan Bharati, the secretary, have agreed to become be our chief speakers and chief guests and guest of honor. And I'm happy that the Jigyasa team has very in a short notice brought out a very nice program for IISF 2021. I wish grand success, and I hope that we will have many such program before the 30th, before the IISF 2021 actually happens in December month. And we could have more program, and around same time also we can have program here at Odisha, so that we can cater to the people of Odisha and adjoining states in terms of the knowledge or enhancement of knowledge. Thank you.
Thank you, sir, for your encouraging and motivational words. Now, it's a great privilege to have with us Sri Vivekananda Pai ji from Vigyan Bharati. Sri Pai is an architect by profession. He completed his B.Arch from College of Engineering, Trivandrum, presently based at Kochi and running own architectural practice. He is currently the National Secretary of Vigyan Bharati since 2010. He is also a part of the team that organized the nationwide Urja Yatras and the India International Energy Summit at Nagpur in 2011. Involved in activities related to sustainable development, especially in renewable energy and green buildings. He was the executive editor of Science India magazine for 2 years during 2008 to 2010. Presently, a member of the advisory board of Science India. Now, may I request Sri Pai ji to address the audience, please. Sir, please.
धन्यवाद देवी प्रसाद दास जी. Honorable Director of CSIR-IMMT, Professor Sundar Satwa Basu ji, Professor Vedanga Das Mohanty ji, Manas Kumar Dalal ji, and Vikas Jena ji, my colleague in Vigyan Bharati also. I am really extremely glad to that IMMT is today conducting this outreach program on a very important day as far as Indian science is concerned. That is the birthday of Acharya Jagadish Chandra Basu. And we are having this program as our Honorable Director mentioned, and in the introduction our Devi Prasad ji also mentioned. Can you hear me?
Yes, sir.
You are audible.
Yeah. Mentioned that as part of India International Science Festival. This program, India International Science Festival, started in the year 2015 as a joint venture between Ministry of Earth Sciences, Ministry of Science and Technology, and Vigyan Bharati. We know that in India is a land of festivals, and we celebrate festivals with all fervor, and many of these festivals convey messages to people in about value systems in such a beautiful way and over the millennia. And these have helped sustain the value systems in our society. And as mentioned earlier by the director also, that translational research and advances in science and technology is what taking a country forward. And India International Science Festival is an occasion to take the message of our excellence in science, whatever we have achieved, to take it forward. And that is why we are conducting this program, which includes various activities. So before coming to those activities, I would like to just mention that this year the IISF is also being organized in a year which is the 74th year of Indian independence, Bharat ki Swatantrata. And as suggested by our Honorable Prime Minister, we all are celebrating Azadi Ka Amrit Mahotsav. And by the next August 15th, that is August 15, 2022, we will be we will be entering the 75th year of Indian independence. Our independence was the culmination of a long struggle against invaders. It was almost a continuous invasion that our country faced, and Britishers were one of the last to leave. And our generation at that time, they fought really hard to drive the British away. Of course, the Portuguese was the last to leave in 1961 from Goa, but that was a very small area that was left. And in 1947, most of our country got independence from the Britishers after 190 years of British rule. It was in 1757 at Plassey War that the Britishers first got hold of political power in the country. So our Prime Minister, during his speech from the Red Fort on the 15th of August 2021, he mentioned some key points about the Azadi Ka Amrit Mahotsav. One was about freedom struggle. That is the struggle that our young and old, they undertook in different ways to drive the British away. In a way, our freedom struggle was not just for a struggle for political power, political independence, but we call it as Swatantrata, which means Swatantrata. Swa means the identity of the self. So the invaders invariably, what they try to do is they try to impose their identity on the subjugated population. Today I am talking to you in English. Actually, this is a language which is so far away, around 6,000 kilometers away. And Bhubaneswar in Kochi, it is just about maybe 1,500 kilometers. But ये एक दुर्भाग्य की बात है कि थोड़ा हम आज इतने स्वतंत्र नहीं हो पाए कि हम अपनी भाषा से बात नहीं कर पाते हैं। ज्यादातर हम मुख्यतः उच्च शिक्षा के स्तर पर, शोध संस्थान के स्तर पर जो शोध हो रहा है, उस स्तर पर ज्यादातर तो अंग्रेजी का ही उपयोग हो रहा है। वो एक परतंत्र तो है ही, पर जो स्वतंत्रता की बात हुई थी उसमें अपने स्व का एक अपनाना, ये एक सबसे महत्व बिंदु था। इसी कारण से बहुत सारा ऐसा कार्यक्रम हुआ कि खादी का कार्यक्रम हुआ कि हम अपने वस्त्र अपनाएं, और जो सॉल्ट सत्याग्रह हुआ, इस प्रकार के बहुत सारे उस पर संघर्ष हुए जो अपने स्तर पर अपने स्व को अपनाने का काम किया। और जो विदेशी थे उन्होंने ये किया था कि अपनी भाषा, अपनी भूषा, अपने रीति रिवाज, अपने कला, और अपनी जो जैसे अभी बात हुई कोरोना के काल में हमने हमारे शोध संस्थान ने कितने अच्छी तरह काम किया। ये जरूर ठीक है कि हमारी पूरी संस्थाएं जो रिसर्च एंड डेवलपमेंट लैब्स हैं और जो हमारा मेडिकल सिस्टम है, इतने अच्छी तरह से किया कि लगभग आज 2-3 दिन में 125 करोड़ टीकाकरण संपन्न हो जाएगा। ये एक छोटा सा मामला तो नहीं है, इतना बड़ा हमने किया है। और हम सब जानते हैं कि अभी भारत एक विकासशील देश, a developing country. We are saying that India is a developing country. And when even the developed world is struggling to fight corona, even today I always keep an eye on what is the number of active cases in India and in some other countries. I see that today we are around 103,000, whereas in the US it is 94 lakhs. It is nothing to like compare or anything. It is unfortunate in many parts, but we have been able to somehow manage, though with some very difficulties during the second wave. So uh, the 5 points that Narendra Modi ji talked about was, one was freedom struggle, which we say just not azadi but swatantrata, where we wanted to attain our identity. And in this case, this time in the India International Science Festival, we are giving a focus on India's scientific community, scientific fraternity, including the individual science movement, scientific institutions, how they played an important part in our struggle for Swatantrata. And the second point that Narendra Modi ji talked about was about ideas at 75. That is now we are at 75, and now how we can plan so that Bharat can be a Vishwaguru by when we are at 100 years as an independent nation. And then about achievements at 75, what are we have achieved, and the actions that are required at 75 so that we actually implement the ideas that we come across, and resolves that what all the things we have to resolve for ourselves, that we will take these actions to make India Atmanirbhar and prosperous. So these were the 5 points that Pradhana Mantri ji mentioned during his talk on in the beginning of Azadi Ka Amrit Mahotsav. And these are the key points based on which our IASF is taking place this year. And we are also happy that this year, apart from Ministry of Science and Technology, Ministry of Earth Science, which is the nodal ministry this year, we also, and other organizations like DBT and other Ministry of Renewable Energy, etc. This year, we also have Department of Atomic Energy and Department of Space. They are also coming in a big way to participate in this program. Now, talking about our Honorable Director Siddha Sato Bajsuji talked about how innovation, science and technology play an important role in making a country, taking a country forward. I would just like to mention about how Indian economy was one of the prominent pillars of the global economy till about 1750. That is, India had almost 1/5 to 1/3 of the global economic GDP till about 150. If we go and Google about Angus Madison, he has made a comparison about global economy from first year of this common era to 2000 common era. We can see that in the first 18.5 centuries, India and China were contributing more than 50%, and India invariably had around 20% to 30% of global economy. In 1757 also, it was just about 20%, slightly less than 20%. But in 1947, when they left, Indian economy was just about 4%, less than 4%. So that is the kind of impact that the British rule had on India's economy. And now many people have quantified, our own foreign minister Jaishankar recently mentioned that in 190 years about, they might have taken away around $45 trillion from India. We are now talking about making India a 5 trillion economy by 2025 with our present GDP at less than $3 trillion. So we can just imagine around $45 trillion being taken away from India. It is, all those stories are known today, but I will just mention just in a very fastly about how Indians acted in this thing situation, because we know if we go to the various institutions of science that Britishers started in 1767 itself, just 10 years after the Plassey War, they started the Survey of India, which was basically like they wanted to survey, they wanted to know which all are the other land parcels that they are going to conquer. And we are, if we look at the Survey of India website today, they will say that it is the first institution of modern science in India. But that was established like that survey of Botanical Survey of India, Geological Survey of India, Zoological Survey of India. These are all resource mapping institutes that the Britishers started. At the same time, they were not very intent on allowing any meaningful research that is taking place in India. So when Jagdish Chandra Basu came back in 1884 from London, uh, the Presidency College Authority said Indians are not capable of doing science in an exacting manner. So we will pay you only half the salary. J.C. Basu said, Jagdish Chandra Basu, whose birthday falls on 30th November, he said, I will teach, but without taking any salary, because you are not saying Jagdish Chandra Basu is not capable of doing science in an exacting manner. You are saying Indians are not capable of doing science in an exacting manner. So he protested in what we may call in a resolute but non-violent way. That is what we call as satyagraha. And for 3 years he carried on like that. And then the Britishers had to accept their failure. Then I will just mention one more name, Prafulla Chandra Rai. As our director mentioned, that translational research is the need of the hour. Actually, Prafulla Chandra Rai established the Bengal Chemicals and Pharmaceutical Works in those 1900s early. And today, when COVID came, we had in the social media this message about how hydroxychloroquine was being produced. Actually, he didn't find it. He didn't develop it, that molecule. He developed mercurous nitrite, and he was known as the man of the nitrites. But he established around 37 industries, and the idea behind that was that we need exactly this translational research. Whatever scientific research that we are doing, they have to be implemented. We have to make industrial progress. We have to establish industries. So in the 1900s, India could produce around 5 to 6 great minds of the science, like including the first Nobel Prize in Science outside Europe, that was in 1930 by Chandrasekhar Venkatraman. We all know about him. And he did his research at Indian Academy for Cultivation of Science, which was established by Mahendra Lal Sirkar. It was, even today, if we go to the website of Indian Academy for Cultivation of Science, we can see that it is mentioned that it is solely native and purely national. And he established it as as institute of science for doing research for Indians by Indians. So this is the context where we are having this campaign also about Swatantrata Sangram and science. And we are also planning to have discussions and debates and talks on this aspect also as part of the India International Science Festival, as already mentioned, from December 10th to 13th. But apart from that, we are having a large number of competitions. Actually, we have a competition in Engineering Students Festival, Science Literature Festival, International Science Film Festival of India. Then we have an activity called Science Village, where this time mainly students from Goa will be physically present, but on virtual mode, students from all over India will be participating. Then we have a traditional arts and traditional crafts and arts festival. We have been conducting achieving Guinness Book of World records for the past 6 years, and this year also around 3 Guinness World Record programs are there. One of them is like around 1,500 teams will be doing an experiment of Gaganyaan, which is being sent to space by ISRO next year. So that is another program. And we also have games and toys. Global Indian Scientists and Technocrats Fest, EcoFest, New Age Technology Show, National Social Organization and Institutions Meet, and also finally a Mega Science and Technology Expo. So I request all of you to register on scienceindiafest.in because this time we are going for a hybrid mode in view of the corona, and around 25% will be physical and 75% will be virtual. So I request all of you for joining this program as at least in the virtual mode, and I am extremely thankful for to IIMMT and Jigyasa for giving me this opportunity to present about IASF 2021. This is a festival of science that we have to take to as a very important science and technology CSIR organization. I hope IIMMT will also do its bit in taking this festival forward. Thank you. Namaste. Dhanyavad.
Thank you very much, sir, for your encouraging and motivational words in the progress of Indian science and technology. So now, may I request our Jigyasa coordinator, Dr. Devi Prasad Das, who is the main person actually behind this program, this outreach program. So now I would like to request him to address the audience. Please, Dr. Das.
Thank you, Manas. Respected our director, the chief patron of this program, our invited speaker, Professor Vedang Das Mahanti, our guest of honor, Mr. Vivekananda Pai, my colleagues Manas and Vikas. Actually, we wanted to do something. Every time all scientists are in a mindset that something we should do for our society. This is our scientific social responsibility. You know, Jigyasa is a program, though the name is coined by centrally, but about 70 scientists actually joined me for contributing to the Jigyasa program in a project mode. So we have been working and designing different types of programs, and this is one of them, IASF Jigyasa Outreach Program, in which we wanted to listen to a very, very eminent personality of our state, Professor Vedang Mahanti, who is a Santiswaru Bhatnagar Awadi, and a lot of laurels are there attached to his name. So we all are interested, sir, to listen to you, and we are thankful that Vivekanand sir told about the IASF and what is the need of present day technology or scientists to do for the India's Swatantrata. Swatantrata means uniqueness. So we have to be unique. In the sense, our science should be unique, our technology should be unique. We should not be just followers. We should not be just copy-paste kind of scientist. We should develop something beyond thinking. Okay, so we are into the line. CSIR-IMMT is doing very well in the research front, contributing a lot to the region in terms of mineral material processing. And when I see the textbooks of science today, even I also tell everyone of here to just go through the science books of class 6, 7, 8, 9, 10, Odia medium or Hindi medium or any medium. You will find they're writing activities. So activities are there in a box. Bring a magnesium ribbon, burn it in a Bunsen burner. Where from a person get a magnesium ribbon? Why it is written in the book? If it is written in the book, it is the responsibility of the scientist to bring those magnesium ribbon to the school. So this is what is our main aim. So we are targeting that we are going to make a lot of virtual materials with all the actual items in place, then carry out all the experiment present in the book, and we'll make it available physically to some extent. And mostly it will be all the activities in the books should be converted to videos and animations. And this is our target for this particular financial year. And we need support from everybody, from Vedang sir, NISER scientists, the students of the state, the engineering college students, school children, teachers. So everybody's well wishes and immediate support is very much required. And our director is giving full support and independent responsibility to all of us, and that is how we are progressing. Thank you very much, sir. We want to listen to Vedang sir. Thank you.
Thank you, Dr. Das, for nice words and good ideas actually to carry forward our Jigyasa program to our school or college students. So now, yeah, so it's a great privilege to for all of us. Our chief guest, Professor Bedangdas Mahanti, and the keynote speaker of the event is with us. So one of the most popular scientists of Odisha, not only Odisha, in India as well as internationally, he's quite famous. And whole Odisha actually always feel proud of him. Before going to listen his talk, let me give a brief introduction about him, though actually he has a large CV. However, with limited time, I can read only a few of the important achievements. Professor Bedangdas Mahanti is currently a professor of physics and dean of faculty affairs at School of Physical Sciences, Niger, Bhubaneswar. He is the spokesperson of India Alice Star Experiments. He was a scientific associate at the Experimental Physics Division, CERN, Geneva, working in Alice. He is a member of the Super CDMS collaboration for dark matter search and Athena experiment at Electron Ion Collider facility in Brookhaven National Laboratory, USA. Professor Mahanti did his masters from Utkal University, Bhubaneswar in 1996 and was a gold medalist, and PhD from Institute of Physics, Bhubaneswar in 2002, and he received the top position, and which is awarded by, which is called LK Panda Fellowship, and postdoc at different laboratory like Lawrence Berkeley National Laboratory, LBNL, USA. He was at the Variable Energy Cyclotron Center, VCC, Kolkata during 2002 to 2012. Some of the recognitions for his academic excellence includes Fellow of American Physical Society 2020, DST Jesse Bose National Fellowship 2017, Fellow of all three National Science Academies 2017 in India, and the Great Santiswarup Bhatnagar Award in Physical Sciences in 2015. He also has been awarded Swarna Jayanti Fellowship in 2010-11, DI Outstanding Research Investigator Award 2010, DI Young Scientist Award 2006, INSA Young Scientist Medal 2003, and he is the editor of the International Journal of Modern Physics E. So with this brief introduction, now I would like to request our chief guest, Professor Mahanti, to start the talk. Please, Professor Mahanti. So the thing is, if anybody having any question or queries related to the topic, just I request all of you actually can write in the chat box, either in MS Team chat box or in YouTube chat box. Then after the talk over, I'll read and just forward to the speaker. Then speaker will try to reply all the queries. Thank you. Professor Bedang Mahanti, please.
Thank you, Manas. Can you hear me?
Yes.
Okay, thank you. First of all, thank you to IISF, Jigyasa, CSIR-IMMT for giving me this opportunity to talk about recent discoveries in physics. I'm from NICER, which is an institute now located in Jatni, whose theme is knowledge imparts immortality. So let me come to the topic of today's talk. The two scientists whom we all know, and one of the most famous scientists of few centuries is Isaac Newton and Albert Einstein. And what I'm going to talk about is related to some of the work which they did 100 or more than 100 years back. We, in the last 10 years, have done some very interesting discoveries in physics. In 2012, we came to know what is the origin of mass. Remember, mass is something which Newton defined in his book Principia, as quantity of matter. In 2015, we discovered gravitational waves. And in 2019, we photographed black holes. These were, I would say, unfinished symphonies of Newton and Einstein, which took such a long time to figure out ways to do it, that needed a tremendous advancement of technology to achieve these basic science goals. So let me start with the discovery of gravitational waves. All of us are taught in schools and colleges this equation which is in the middle, that there are two masses, m1 and m2, separated by a distance r, and the gravitational force is g m1 m2 by r square. But that time we didn't realize that there are some issues with this. The issue is that this given by Newton treats space and time as separate. There is a concept of absolute motion, and the interactions are instantaneous. There is instantaneous action at a distance. Subsequently, Einstein put space and time together. Special theory of relativity and general theory of relativity came into picture. He brought in the concept of relative motion, and he said that the gravity, as we understand from Newtonian concept, is actually a special case of a more general concept. Gravity is a wrappage of space and time and is not action at a distance. The information is carried by mode of gravitational waves, which travel with speed of light. Remember, you must have read in relativity that no signal can travel with more than speed of light. So this equation that you see cannot be instantaneous. So there is a way by which this force message is carried, and that is through gravitational waves. But they were not discovered. But how to visualize the concept of gravity from Einstein perspective? Remember, from Newtonian perspective, it's instantaneous action at a distance. As soon as two bodies come close by, put at a particular distance, they will immediately know that they have to interact gravitationally. But that's not what is allowed from principles of relativity. Finite time is taken by the signal. Now, Einstein imagined space to be a stretched rubber sheet, and a mass on the surface will cause deformation, as you see on this picture on the right-hand side. When another mass is dropped on the sheet, it will roll towards it. So that's what Einstein theorized, that smaller masses travel towards larger masses, not because they are attracted by some mysterious force, but it is because smaller objects travel through space that is wrapped by the large object. So that's the concept that he gave about gravity. Now, is this correct? Is the space and time have a curvature? So in Einstein's theory of relativity, anything which has energy has mass. Mass in the sense that it is attracted gravitationally. A massive object shifts apparent position of the star. By that what I mean, that suppose you are looking at a star far away and there is a massive object in between, then the position of the star would be shifted because the space-time has a curvature. Light would bend. It's like a lensing effect. The way you see in common lens, that is called gravitational lens. This was the concept that, and Arthur Eddington set about trying to see if that's true. So what he did is he chose the day of solar eclipse. So we have Earth, the sun, and sun is in between a star that he wants to see. And because of solar eclipse, all the lights that is coming from the sun is not there. And then he tried to see where is the position of the star. And then he compared it with the position of the star when sun is not in between. And that's how he could prove that light indeed bends. Remember, light, which is composed of particles called photons, which are massless, but they have energy, and the light bends. And this is the picture that he saw about that one sees from gravitational lensing. Although the position is at the center, if there is a massive object, the apparent positions that one observer sees on Earth is different because of lensing effect. In this he found in 1919, and he popularized it by writing down a poem which reads like this. O live the wise our measures to collect. One thing at least is certain, light has weight. One thing is certain and rest debate. Light rays when near the sun do not go straight. So that was one of the proofs of this concept of rappage of space-time and gravity. But the gravitational waves were not discovered. Now, we know that whenever a charged particle is accelerated or decelerated, it emits radiation or photons. Similarly, the gravitational waves are radiations due to accelerated masses. How does this acceleration happens? When the space-time curvature shrinks along particular directions, as is seen in this cartoon on the right-hand side. So if the space stretches and expands, is there a question?
No, please go ahead.
Okay.
No.
So then this leads to gravitational waves being generated. Remember, Eddington showed that light bends. And now, if there is shrinkage of space in one direction perpendicular to the other, you could also generate waves called gravitational waves. How would one detect such a gravitational wave? There could be many sources of gravitational wave. There could be collisions of huge astrophysical objects like neutron stars or black holes. They could merge together, and that would lead to ripples in the space, and that could lead to gravitational waves. But how would you detect it? The principle is based on what is called Michelson interferometry. This is one topic which students read when they take up special relativity. In this, the experiments is actually done by undergraduate students in UG labs in NICER, and the setup I have shown on the right-hand side. The technique is very simple. You have a source of light, the laser, and then there is a mirror 45-degree inclined. When the light comes, it splits into, it goes to the two mirrors, mirror 1 and mirror 2, and then they come back and then they fall on the screen. This process results in a path difference, which causes a phase difference, and that leads to an interference pattern. And this interference pattern is what you see on this right-hand side screen in an undergraduate laboratory. Now, the two waves which are coming from the two mirrors, they can interfere in phase or out of phase. If they are in phase, then it will lead to a resultant wave which is much larger in amplitude. if they're out of phase perfectly, then the crest and troughs will cancel each other and you will not get anything. So what's the idea of detecting gravitational wave? One would set up such a interferometer, and what would happen is that you have a source of light and you set up this interferometer, and you could put it in a condition which is either out of phase, or you could put them in phase. And then what happens when a gravitational wave passes through us? It changes the length of these arms. As a result, the pattern that you set, the baseline that you had set, changes. Suppose you were in perfectly in phase and the gravitational wave passes through, then the length of these interferometer arms changes because things are passing through the space. As a result, the pattern gets disturbed. The challenge is the lengths change by a very small amount. So you need to have highly sensitive instruments to detect it. The change in arm length is of the order of 10 to the power minus 18 meters. Remember, you are doing an experiment to detect changes in length scales of the order of 10 to the power minus 18 meter. That's where the technology comes in. That's why it took a long time to set up this experiment. Just to give you an idea of what I mean by 10 to the power minus 18 meters, 1 meter is about 40 inches. Human hair is 10,000 times smaller than a meter. The wavelength of light is 100 times smaller than the human hair. The atomic diameter is 10,000 times smaller than the wavelength of light. The nucleus, which is present inside the atom, has a diameter which is 100,000 times smaller than the diameter of an atom. And we are telling that we have to detect length scale which is 1,000 times smaller than a nucleus inside an atom. That's the technology which needed to be developed. And it was done through an experiment called as LIGO. There were 2 such Michelson interferometry based experiments put up at Hanford Observatory and Livingstone Observatory. They were 10. The observatories, the Michelson interferometer, the lengths arms were 4 kilometers long, and they did detect gravitational wave. I will show you in this video the signal that they saw, and the signal was converted into sound, and you can see what they detected was profound. They actually detected 1.3 billion years ago 2 black holes which collided. This is a simulated version of it. 1.3 billion years ago 2 black holes collided, and the signal has been passing through our universe, generating gravitational waves, and it reached us recently in 2015. So here is a simulation which shows that the 2 black holes, as they come closer to each other, they circle more rapidly and then they collide and the gravitational waves are generated. It's reached LIGO. That's the sound of the waves when converted to this form is what you hear. Remember, what you are hearing here is the signal converted to sound coming from 1.3 billion years ago. Isn't it a profound discovery that we could detect gravitational waves coming and reaching us 1.3 billion years ago from a collision of 2 black holes? Of course, it was such a big discovery that it came up in everywhere, in all newspapers, that it got worldwide media attention, and rightly for the discovery of the observation of the gravitational waves in 2017, Nobel Prize was awarded to these three gentlemen. So we are living in an era which saw the gravitational waves, and we are really lucky about it. Now let me come to the origin of mass. All of you know that atom consists of a positively charged nucleus. The nucleus are made up of protons and neutrons. The protons and neutrons, as we know today, are made up of still smaller objects called quarks. So far, there are no substructures, or quarks are not made up of something more smaller. So the quarks, the gluons, and the electrons are the fundamental particles all of us are made up of. Anything that you see in this visible universe are made up of electrons, quarks, and gluons. How did people figure this out? It was a very young scientist in his PhD thesis, D. Broglie, who gave this equation: lambda is equal to h by p. P is the momentum, lambda reflects length scale. What it tells us that if you impinge high momentum particle, then you can probe small length scales. Higher the momentum, smaller the length scale, it probes. That is how what if matter is made up of was figured out. And we know today that it is made up of electrons, quarks, and gluons. Now the question is, we all have read electron has a mass which is 9.1 into 10 to the power minus 31 kilograms. Question is, who gave electron this mass? Well, we can actually ask, what would have happened if electron did not have this mass? Suppose, you know, it is 0.3091 kg. For any ordinary persons like us, we could just take it as 0. But what would happen if it was exactly 0? This is an expression students must have come across in relativity. What I'm asking is, suppose a particle has 0 mass, m0 is 0, but energy is not 0, E not 0. When can this expression be satisfied? This expression can be satisfied when V equal to C. So all particles which have mass 0 and energy not 0 have to move with speed of light. So if electron would have had mass exactly 0, then it would have moved with speed of light. If electron would have moved with speed of light, then atom could not be formed. Molecules could not be formed. Compounds could not be formed. We won't exist. The visible universe that you see exists because electron does not have 0 mass. It has a finite mass, although very small. So you understand how important it is to understand that why electron has this mass. Who gave electron the mass? What is the origin of mass? Imagine the other situation. Suppose the mass would not have been this exact value. It would have been 1,000 times smaller or 1,000 times larger. What would have happened? All of us have read the Bohr's theory of atom. And in that, the radius of the Bohr orbit is inversely proportional to the mass of the electron. So you can see if the electron mass was 1,000 times smaller or larger, the radii of atom would have been different. We would have been hundreds of meters long, or we would have been several microns smaller. The universe that you see would not be the same. There would be bigger people, bigger building, bigger structure because the atom became big, or that would be smaller building, smaller structure because everything shrunk. So the fact that electron has this mass gives whatever you see is the right proportion and size which we are now acquainted with. So what is the origin of these masses of these fundamental particles like electrons or quarks? In order to find that, the Large Hadron Collider was built. Now I want to tell you in a simple way how mass is generated. For that, I have to tell you what is called a field. Field is a technical term in physics. So I will use analogy to explain to you the field that we talk about in physics. Remember, it's a simple analogy. The things lies in details. Let's consider the wind as a field. Wind is something that is all around, right? So wind is something which exists everywhere. Somewhere we do not feel it. Somewhere we feel it. Suppose you are near a table fan, you feel it, right? And the waves associated with it causes sound. So what's a field? Field is like a wind. Field is something which exists everywhere. Somewhere it is zero, somewhere you feel the wind, somewhere you do not. Somewhere it is not zero and is associated with a wave. But if it's a quantum field, then a wave is associated with a particle. So a quantum field has a particle. So what's a field? Analogy, exists everywhere, somewhere zero, somewhere not zero, has a wave and is associated with a particle. Let's take an example of the electromagnetic field, which all of us are familiar. Does it exist everywhere? Yes, it exists. Otherwise, mobiles won't work, right? Now, is it somewhere zero and somewhere not zero? Yes, it is zero because we don't feel it. But suppose you bring in some disturbances, electrical disturbances, then you find you cannot watch your TV because it interferes. What is the wave associated with it? The light waves. And what is the particle? It's the photon. So see, so the electromagnetic field falls in our definition or analogy definition of a field. Similarly, people thought, hypothesized, there is a Higgs field. What's a Higgs field? It exists everywhere. Somewhere it may be zero, somewhere it may not be zero. It is associated with a wave and the particle is called Higgs particle. Only difference it cannot be zero. If it were zero, then electron would not get its mass. So how is then the mass generated? What it has got to do with Higgs field? But before I go to that, remember, in order for us to prove that there is a Higgs field, it is sufficient to prove that there exists a particle called Higgs particle. Because a field is associated with a wave and a quantum field has a particle. So to discover Higgs field, it is sufficient to discover a Higgs particle. Remember this point. Now let me go and tell you why it should not be zero. How is mass generated? Now this question was asked to scientists. Can you explain in a layman term how mass is acquired by electron or the quarks? The best one will be awarded a bottle of champagne, and the best prize went to Professor David Miller that time from University College London, and his analogy is what I will describe to you. Imagine a room which is filled with a political activists. Now an important person like the Prime Minister or President walks in. What would happen? Everybody would like to meet and greet, would like to exchange views, would like to give him representation. So remember, the person enters and then there is a group of cluster of people formed. This is the analogy of how mass is acquired by a particle. There is Higgs field, electron enters the field, okay, and the amount it interacts with the field, more is its mass. More are the interaction means more is the cluster of people. Similarly, more is the interaction of electron with the field, more would be its mass. Electron interacted little less, so it got less mass. Some quarks interacted more, so they got more mass. So mass is generated through interaction. Now let's come back to the same analogy, come back to the same room. Somebody comes in and tells an interesting rumor. For example, you know, Sachin Tendulkar returned back to cricket and scored 500 runs in a day. So what would happen? People would cluster together, the people in the room would cluster together and start interacting, discussing, looking at the mobiles, looking at the news, right? So what is this analogy? The field interacts among itself to generate the particle called as the Higgs particle. If we discover Higgs particle, we know Higgs field existed, then we know how electron got its mass because it interacted with the Higgs field. So that's what led to the building of Large Hadron Collider. It took 50 years to discover the Higgs particle since it was hypothesized, and you need a lot of engineering, science, technology in order to build this machine. It's the largest particle accelerator in the world with a circumference close to 27 kilometers, spanning almost the distance from Cuttack to Bhubaneswar. You needed 9,300 magnets to be kept at minus 271.3 degree Kelvin centigrade. Remember, it's so close to absolute zero, even colder than outer space. Imagine the technology needed to make these superconducting magnets and keep them working to achieve what we are looking for in basic science. The pressures in the beam pipes, which will carry the two protons, which will be collided to convert energy into Higgs. The pressure has to be 10 to the power minus 13 atmosphere, 10 times less than the pressure on moon. Imagine the science and technology needed to create this pressure. Two protons come and collide, and the energy is pumped in, which leads to creation of a particle of mass like Higgs particle. To reach that high energy, a proton has to move this 27 kilometers, 11,245 times a second. 27 kilometers has to be covered 11,245 times in a second. That's the fastest, perhaps, racetrack known to mankind. Imagine the technology that is needed to do that. The matter which is produced with this collision reaches temperature which is 100,000 times larger than sun. I'll come to that. And the data that comes out, the big data that comes out, will fill up 100,000 dual layer DVDs every year. That's the machine which needed to be built to discover what is the origin of mass, to discover Higgs. Once you discover Higgs, you know the Higgs field exists. Once you know Higgs field exists, electron must have interacted with Higgs field to get its mass. How hot is this matter? Remember, such a hot matter only existed in the early universe. You can see on the right top corner, this is the evolution of the universe, and temperatures of the order of 10 to the power 15 to 10 to the power 12 degree Kelvin existed in a microsecond old universe. We are trying to replicate that condition in the laboratory. Temperatures of the order of 10 to the power 12 to 15 degree Kelvin. How does it compare? This is the world's lowest temperature recorded. These are 10 to the power minus 6 degree Kelvins are temperature obtained in trapped ion systems. 3 degree Kelvin, 2.7 degree is the universe temperature. 300 degree Kelvin is the temperature in your room. 6,000 to 10 to the power 6 degree Kelvin is the temperature range in the sun from its surface to the interior. 10 to the power 9 degree Kelvins are temperatures which are reached when neutron stars collide. And what we achieved at the Large Hadron Collider is 10 to the power 12 degree Kelvin in order to discover Higgs particle, to understand this basic mechanism of origin of mass. So I will then show you a video of how this Higgs was discovered. Remember, it's a class of particle called bosons. Boson named after Satyendranath Bose, who actually, along with Einstein, proposed this class of particles called bosons. So we will start the video. So LHC is situated at CERN laboratory, which is in Geneva. It actually borders Switzerland and France. This is the Large Hadron Collider. Everything starts with an hydrogen bottle, which is ionized. So you have protons. The protons are accelerated through a linear accelerator, then fed to a larger accelerator called proton synchrotron. Then it goes to the proton synchrotron booster. After that, it is fed to the proton synchrotron PS. After it reaches a particular stage of collision energy, then it is fed to a larger ring, the super proton synchrotron. That's where I did my PhD. When it reached a higher energy scale, it is fed to the Large Hadron Collider. There are two beams moving in counterclockwise direction. Using magnets, they are made to collide at centers of detectors. These detectors detect the collision debris. And there are four such major experiments: ATLAS, CMS, LHCb, and ALICE. The protons come and collide. The collision debris are detected on the detectors. The data is transmitted to a data server where they are initially processed, and then it is transferred to a data center which should be accessible to people working in 120 countries. That's how World Wide Web was born, so that we could share data among all peoples working in this experiment. And this data computing power was so large that we have to make grid computing, like an electrical grid connecting all the computers across the world. We reconstruct the event which produced this Higgs particle. You fill the histograms of mass of the particle coming from decay of two photons. The histograms are getting filled, and this blip that you see is the proof that there is Higgs boson. And that's how on 4th of July 2012, the Higgs boson was discovered, and subsequently we have now understood several of its properties. With the discovery of Higgs, we now know how particles got mass, origin of mass, and we know how we exist. Of course, it will bring in worldwide media attention, and rightly, Nobel Prize was given in 2013 to the theoretical colleagues who proposed this idea of how electron and subatomic particles have their mass. And there is also the mention of the experiments that was carried out which discovered this predicted particle. Indeed, we are living in an era where we are very fortunate to see these discoveries. Finally, photographing the black hole. Now, black hole has fascinated many people, including Subramaniam Chandrasekhar, the Nobel laureate who has done pioneering work on it. How do I understand? From a very simple perspective, this is the escape velocity which students must have read in +2. Now, if I put instead of VE speed of light c, that means nothing can come out of an object with mass m and r, which satisfies this relation where VE is c. Nothing can escape, right? So that is an object we are talking about. If nothing can escape out of it, how do we photograph it? Well, the Event Horizon Telescope collaboration imaged the black hole. And what you see on 10th April 2019, they released the picture of the black hole. How did they do? Well, nothing can escape out of it, but they can get the boundary by looking at things falling into it. So the ring of fire that you see, the red color, is coming from gases falling into the event horizon, and whose shadow is the black hole at the center. So this is the idea with the trick which was used by Event Horizon Telescope to photograph something which is present at the center of all galaxies, including our galaxy, the Milky Way. For that, one had to have telescopes put almost half of the globe. A network of telescopes across the globe was put in order to picture this black hole, something which people never thought one can photograph because nothing is coming out of it. The general theory of relativity techniques, the equations were used in order to process the data in order to get this image. And no wonder it again got worldwide media attention. In 2020, Nobel Prize was awarded to these three professors for their pioneering work in the field of black holes. So now I'm coming to my summary. We are really lucky to have seen three most profound discoveries of the century. In the last 10 years, we know how electron got its mass, quarks got its mass. We discovered Higgs boson on 4th July 2012 and understood origin of mass. We understood how gravity works, something without which we cannot walk. It's the force responsible for moon going around Earth, Earth going around sun. The story was completed with the discovery of gravitational waves on 14th September 2015. Something which fascinates all of us, the black holes. We never thought we could photograph it, but that challenge was overcome on 10th April 2019 when we really saw a black hole, we photographed it. These are the profound discoveries which has happened, some of the profound discoveries which has happened in physics in recent times. I will end by this with this quote from C.V. Raman. This is to the young people in the audience. He, while giving a lecture at one of the outreach programs, once said, "Youth is the most glorious time of all. I have said elsewhere that most of the great discoveries in science have been made by young people. It is not the experience or wisdom that the old age brings, but the freshness of outlook, the indomitable desire to achieve, which is the characteristics of youth that makes discoveries possible. It is this that makes life worthwhile. If only you realize this, and you realize that here I am still young, let me see what I can do, that all discoveries become possible." I'm sure some of you will discover many fascinating things in science and physics. Thank you. Thank you very much.
Thank you very much, Professor Mohanty, for the wonderful and outstanding talk. So now it's the time to take a few questions, either from MS Team side or from YouTube side. The first question I'll read. It is from YouTube. Why ordinary matter is affected by gravity?
Yeah, so there are four basic interactions in nature. One is called gravitational interaction. It happens when objects have mass, or as you saw from general relativity, has energy. Electromagnetic interactions, if it has electric charge. Weak interactions, which gives rise to phenomena of radioactivity. and strong interaction if it has something called color charge. So these are the four fundamental interactions in nature. If you ask why these are only the four forces, I do not know. But these are the four basic forces that is there in nature. And one of them is gravitational force.
Okay, next one is from Dr. DP Das. How temperature were measured? Very low and very high temperature cannot be measured by sensors like thermocouples.
Yeah. High temperature one, I will like to say, as you rightly said, when matter itself melts, what sensor can we use to measure it? So one takes help of statistical mechanics. One looks at the particles which are coming out of this collisions, and if it's an thermal distribution, its production, if you measure the energy of the particle in x-axis and its number or probability in y-axis, and if it's a Boltzmann distribution, then you can write it as e to the power minus e by kt. Now the t is a variable, and you can fit the distribution to get the temperature. So use statistical mechanics to get the temperature.
Another thing actually from our Jigyasa coordinator. So please give some idea about low cost demo models that can be made for students to understand atomic and nuclear physics.
One very important thing that you could really see relativity at work is by measuring muon decay lifetime. And this can be set up. We had an experimental high energy school here at NICER, and one tried to build the muon decay. Muons, cosmic muons are all coming from outer atmosphere. We do not know the origin where they are coming from yet. And if you can detect them, their lifetime you can measure, then you can explain concepts of relativity. For example, this is one thing which comes to my mind. Again, another thing is we could also set up simple Rutherford scattering experiments. Okay, Rutherford used alpha particles on a gold foil to figure out that most of the space in an atom is actually blank. There is a positively charged nucleus. As a result, particles were getting deflected back with most of them passed through, few got deflected, and very, very few got path retraced back. One could also set up that experiment in order to understand atomic physics. So like that, yeah, we could, in principle, set up experiments.
Thank you. Again, actually, with the continuation of with this question, Dr. Das is asking, can we get some video from NICER labs for students?
It's possible. We could do that and share the video. That's a good idea. Maybe some of them already could exist because of online classes. We were showing some of the practicals and recording and putting it for the students' benefit. I will have to check that.
Thank you. Another question from Dr. Siddharth Kumar Pradhan. How do electron and quarks get their charge?
Yes. So what I discussed is how electron got its mass, 9.1 10 to the minus 31 kg. We do not know yet how electron got its charge, 1.6 10 to the power minus 19 coulomb. That has to be figured out. And also why most of the particles that we see are multiples of electron charge. Why there is some other charge, some other fractional charge exists. Those are open questions in physics.
Thank you. So anybody actually from IMMT you would like to interact with Professor Mohanty, most welcome. Directly you can interact.
I'm Dr. Devi Prasad. Actually, I am the Jigyasa coordinator. Your talk was very much enlightening, and we want to take your support and help in future. Basically, I am from electronics background. So I did my BSc in physics and then MSc in electronics. So we can actually use our electronics instrumentation knowledge to help students to develop many experiments. For example, we have a lot of CRT tubes nowadays not being used in computer monitors and all. So can we set up some labs using them for showing the electron gone, and or you can use some vacuum tubes for that sort, because they are not being used, but experiments can be designed like that.
Sure, that's a good idea. I have noted down. Maybe we can discuss more. Since we are close by, maybe we can invite you sometime to NICER, and we can certainly it can be done. And let's discuss more.
Yes,
Okay.
yes, thank you, sir.
So I would like to comment something. I'm Dr. Pradhan. Can this CERN kind of research be done in India, maybe at a lower level?
Yeah, that's a good question. Actually, because of the cost factor, CERN accelerator is not built by one country. They pull together research resources to make it. It's a huge amount of investment. So every country pulled together, and Switzerland was chosen for its history of being neutral. It didn't participate in any of the conflicts. But such experiments, not exactly that, but similar high energy physics experiments can be set up. What we need is, there are two ways to look at it. One is have some underground laboratories. You know, one can use, for example, dark matter search or neutrino physics. There are very interesting topics where you need to shield all the backgrounds and only allow those particles to come into your experimental hall. So the laboratories has to be built underground. We are exploring possibilities of doing this experiment at Jadugada mines, also at a place in Theni in Madurai, and also at Rohtang Pass. These are places where we are trying to see if we can set up these experiments where even people from outside can join and do experiment with us. The other is use our power reactors. Our power reactors are also source of neutrinos. And you can use the reactors and set up experiments to do physics, which is very interesting and with discovery potential. That also we are exploring, and there is some progress in that direction.
Okay, thank you for a very interesting talk and a lot of information. A lot of things I learned. Thank you.
Thank you.
Anybody else? Yes, please go ahead. Hello, Dr. Mamta Mahapatra, please.
Yeah, good evening, Dr. Mahanti. It's really exciting talk, and also a lot of things we need to know. Actually, we also don't know many things. In fact, so we are like a kid, we are understanding the subjects. So out of curiosity, since it is a Jigyasa program, we actually meant for the students, school level students. As you know, now students are running off lot of games and other kind of stuffs through internet, and they are not very willing to learn this kind of stuff what we learn in our childhood. So how can we make some scientific game or physics game like kind of things by you understand, by mutual sharing of our knowledge, so that we can also upload in virtual mode and also we can demonstrate in the school children so that they will more attract towards the science, not towards the other stuffs.
Yeah.
So that is like my request, as I also suffered. My kids are always following all kind
Yes.
of nasty stuffs. I want to get rid of that. As a parent, I'm approaching you. It's not as a scientist. So
Yeah.
how?
I agree. I agree. So there are attempts going on in that direction. Although I am not an expert in it, but there are people who are devoting time to make cartoons to explain its concept. Okay. Another is people are doing some rap music to explain, for example, dark matter. So there are attempts to catch the imagination by doing what you are proposing, and it can certainly be done. But you need also people who can, who has that expertise interacting with scientists, so that you could make that happen. But there are attempts going on.
Can we make in Odisha itself as you know? Can we start together through this Jigyasa program? At least one.
Yeah, it's possible. So either explaining a concept through cartoons or in some way.
Mamata Mohapatra ji, I just want to make a small mention. This is a very important intervention that you have made, that how we can teach science through games and toys. And this is one of the major events for this year's India International Science Festival on there is a, because this year the idea is that creativity in science, that is the theme of this year's IISF. And we have an exclusive a program on games and toys. So I may request you to just join in this time. And it is not just a program, it has to be carried forward. And it is a very good idea if Mohanty ji and IMMT Jigyasa comes together and take it forward. So probably that you will come across a few people who are in this field today in India, which will help you to bring together all the stakeholders. It's a great idea. Congratulations. And I also thank Bedangadas Mohanty ji for such a wonderful presentation. It was really, really nice. And it is not very easy that you convey all these high physics in such a lucid manner, using such very simple, and that David Miller's cartoon and all. You have arranged it in a very beautiful way. We will actually bother you for more talks at other places also.
Well, thank you very much for your kind comments. Thank you.
Thank you, sir. So, anybody else? I think we have taken actually many more questions. So let's thank Professor Mohanty for this wonderful talk and question and answers and discussion with our scientists. So now I request one of our coordinator, Dr. Vikas Kumar Jana, Principal Scientist, CSIR-IMMT, to propose the vote of thanks. Dr. Vikas, please.
Good afternoon to all of you. So respected today's chief guest and keynote speaker, Professor Bedangadas Mohanty, Physical Science, Niger, Bhubaneswar. Respected our National Secretary, Vigyan Bharati, and guest of honor, the Vivekanand Paiji. Respected our Director, CSIR-IMMT Bhubaneswar, Professor Suddhasata Basu. Distinguished guests, my dear colleagues, students, ladies and gentlemen. Really, it is a great honor and privilege for me to propose vote of thanks before the galaxy of eminent personalities witnessing this event. I extend my hearty vote of thanks to each and everyone for gracing this occasion. First of all, on behalf of CSIR-IMMT Bhubaneswar, I express our heartfelt thanks and gratitude to our respected Professor Bedangadas Mohanty for gracing this occasion in spite of his busy schedule and delivered such an interesting talk on discovery of physics.
So we are extremely grateful to you, sir. On behalf of CSIR-IMMT Bhubaneswar, I express my profound gratitude to our respected Sri Vivekanand Pai for gracing this occasion in spite of his occupied time, and also delivered such a thought-provoking talk, and also giving them some interesting information of our India International Science Festival. We are even grateful to you, sir. We express our sincere thanks to our distinguished invitees, those who have joined with us to witness this event. We express our sincere thanks to our director, Professor Suddhasata Basu, for his interaction, suggestions, and encouragement and support throughout to organize this event. I would like to take this opportunity to place a record on sincere thanks to our committee members, colleagues of IMMT for their great support to organize this event. I would like to specially mention the work of our CN and EM department for their great support to arrange this virtual program. So our heartfelt thanks to one and all for participating in this event. So thank you all. Have a good evening. Thank you all.
So thanks a lot, Dr. Bikas Kumar Jana, for proposing the vote of thanks. So now it's the time for national anthem. So all are requested to stand up for the national anthem, please.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
So thank you all. Before quitting the program, thanks once again to Professor Mohanty, Sri Vivekananda Pai ji, Dr. Devi Prasad Das, Dr. Bikas Jana, Professor Basu, and thank you all. So we'll quit the program. Dr. Devidas, will quit the program, or you want to say something?
Yes, sir. Thank you very much. We'll take your help in future, sir. Please extend your help. Thank you, sir.
Okay.
Thank you all.
We can leave now.